All right, everybody. We are going to start lesson one of topic five. This topic is entitled energetics. That means we're going to be looking at thermodynamics and see what that entails. So, lesson one here, this is talking about enthalpy changes. A lot of this will be familiar to you from last year. Here are the understandings. These are the things you are expected to understand in um, topic 5.1. This is what you are expected to be able to do, the skills. So, the first thing we have is energy and heat transfer. So, let's talk about what energy and heat is. Energy, if we had to define it, is a measure of the ability to do work. And work is defined as um, how much it takes to move an object a certain distance against a force. Work is something that you would see a lot in physics. Heat, on the other hand, is a transfer of energy when two systems are at different temperatures. And one thing I want you all to remember is that temperature is a measure of the average kinetic energy of particles. So, a unit that we are going to see quite often in this topic is joules. That is the unit that we are going to use for measuring energy. The definition of the joule, it is a unit of energy and work, and you do 1 joule of work when you exert a force of 1 Newton over a distance of 1 meter. One thing to note, that energy is always conserved in chemical reactions. So, we've heard of the law of conservation of mass. Now we have the law of conservation of energy. Energy will always be conserved in a chemical reaction. Here we have the system and the surroundings. So, when we do a chemical reaction, let's say, heat increases the temperature of a substance, of various substances, in a disordered fashion as opposed to work, which is more orderly. Now, we've talked about how energy is conserved, but one thing that can happen is energy can be transferred. So, when we talk about this transfer of energy, we need to define the system and the surroundings. First of all, we have the system, and that is what we are studying. It could be a chemical reaction, for example. Then we have our surroundings. This is anything that is outside of the system. So the system is going to be our focus, and the surroundings is everything else. Now we have two types of systems. We have an open system. This is one in which both matter and energy can be exchanged with the surroundings. And then we have a closed system, is one in which energy but not matter can be exchanged with the surroundings. Here we have something called enthalpy. Now, enthalpy is given by a capital letter H. Enthalpy is a measure of the amount of heat energy contained in a substance. It is stored in the chemical bonds and intermolecular forces as potential energy. Okay, so enthalpy is one way that we can talk about heat, or how much heat is in a substance. So, when two substances react, the difference in the enthalpy between the reactants and the products results in a heat change which can be observed. So, what that means is the temperature will go up or the temperature will go down. So, the changes in enthalpy are denoted by the symbol delta H, okay, a change in enthalpy. If you have a delta H that is positive, then heat has been added to the system and the reaction is endothermic. When delta H is negative, heat has been released from the system and the reaction is exothermic. These are two Very important things that I want you all to remember. Delta H is positive, endothermic. Delta H is negative, exothermic. So here we have an endothermic reaction. Here we have that the heat, or our heat energy, is being added to the system. And if we look at our graph of a enthalpy of a reaction over time, we see that before our H, our enthalpy, was really low, and after it was really high. So we can see that enthalpy, the delta H, or the change in enthalpy, is positive. Okay, it has been absorbed. And here we have an exothermic reaction. So here we can see our system and our heat energy. It is being released into the surroundings. So again, here we look at our graph of enthalpy over time. Again, we see the enthalpy before and after, only this time the enthalpy before is high and the enthalpy after is low. So our delta H, our change in enthalpy, is negative. Okay, it has decreased. So we can now compare the enthalpy of the reactions. Okay, we take the two graphs that we just looked on the previous two slides, and we can see that for exothermic reactions, heat is given out by the system and delta H is negative. That is what you see on the left-hand graph, letter A. And for endothermic reactions, heat is absorbed by the system and delta H is positive. Okay, so we see that on the graph on the right, letter B. So make sure you can differentiate between the two graphs and you know which is endothermic, which is exothermic. Here we are going to talk about standard enthalpy changes. So we often define the standard enthalpy change for a reaction, which shows how much energy is released or absorbed in a given reaction. So it's one thing to know, is energy being absorbed or released, but now we want to calculate it. So the standard enthalpy change, which is given by the symbol delta H naught, okay, that's the little symbol after the H. It is given in the literature under the following conditions. So we have standard conditions. Pressure is 100 kilopascals. For a solution, the concentration would be 1 mole per cubic decimeter, or 1 molar. And all substances are going to be in their standard states. Temperature is not part of the definition of standard state, but 298 Kelvin is usually given as the specified temperature. Now, it said before that all substances are in their standard state. We define the standard state of a substance as the pure form of a substance under standard conditions of 298 Kelvin and 1.00 times 10 to the 5th pascals. Okay, usually the pure form of a substance will be the solid for a metal, for example, a gas if it's something like oxygen or nitrogen. Now, I'm sure you all are used to chemical equations, but now you're going to start to see information about the enthalpy change. So we can see our chemical equation here for the combustion of methane. But over on the right, you can see that delta H equals negative 890 kilojoules per mole. Now, this is a stoichiometric relationship. Okay, for every 1 mole of methane, it releases 890 kilojoules. Therefore, if we react 10 moles, it will release 8,900 kilojoules, right? It says negative 890 kilojoules per mole. Now, we can say if we react 2 moles of oxygen, how much heat will be released? It's going to be negative 890 because in our balanced chemical equation, that is how much oxygen is required, 2 moles. Now, it is going to be important that we pay attention to the state symbols because the enthalpy change will depend upon the state of the reactants and the products. Now, I want to quickly review what temperature is. Temperature is not the same thing as heat. Temperature, as it is defined, is a measure of the average kinetic energy of a substance, and we usually measure it in kelvins. We've heard of absolute zero before, 0 Kelvin. It is the temperature at which all movement stops. So temperature and heat are not the same thing, and I want you to start to recognize that and remember that moving forward. One of the ways that we can look at the enthalpy change of a substance is to look at something called specific heat. Now, one thing to know is that if we add the same amount of heat to 2 different objects, they will have a different change in their temperatures. So heating 2 objects up will not necessarily mean they will be the same final temperature. In general, the increase in this temperature when an object is heated depends upon the mass of the object, the heat that is added, and the nature of the substance. The amount of energy needed to raise 1 gram of a substance 1 Kelvin is known as the specific heat of an object. And one little hint, one thing I want you to remember, is that the higher the specific heat, the more energy that is required to raise the temperature of that substance. So there is an equation that I want you to become very, very familiar with, and this is the heat change, which is given by the symbol Q, equals the mass, M, times the specific heat capacity, C, times the temperature change, delta T. So we could see Q equals MC delta T. One way I like to remember this is Q equals MCAT. Okay, Q equals MC delta T. Here below we can see the symbols that are given for each of those variables. Okay, heat change is joules, mass is in grams. The unit for specific heat capacity is joules per gram per Kelvin. And then delta T is given as Kelvin here. When we are dealing with water or a solution, which we will see in lessons down the road, the specific heat capacity of water is 4.18 joules per gram per Kelvin. This value is given to you in the data booklet. one thing I want you to note is when considering the relationship between different objects, the heat capacity is often a more convenient property. The heat capacity, which is given by the capital letter C, is defined as the heat needed to increase the temperature of an object by 1 Kelvin. Okay, so one equation here, heat capacity equals the heat change divided by the temperature change. And here's a comparison of the specific heat capacity versus the heat capacity. You most likely are going to only be dealing with specific heat capacity, Q equals mc delta T. Okay, here we have some practice problems. You can see that the answers are on the screen here, but you should try and go ahead and practice these problems first, and then you can check your answers. So we have the question, how much heat is released when 10 grams of copper with a specific heat capacity of 0.385 joules per gram per degree Celsius is cooled from 85 degrees Celsius to 25 degrees Celsius? And here we have a hint. A change in Kelvin is the same as the change in degrees Celsius. So when we are dealing with heat changes and dealing with Q equals mc delta T, it does not matter if the temperature change is given as Celsius or Kelvin. You will get the same answer regardless because you are taking the change in temperature. So we write down what information we have. Well, we know the mass of our metal copper, which is 10 grams. We know the specific heat capacity, so we know C. And we can calculate our delta T by remembering final minus initial. And then since the question is how much heat, that means we're looking for Q. So we're going to do Q equals mc delta T. We plug in what we know, and we can see that Q equals negative 231 joules. Now, one thing to note is that Q in this answer is negative. And this makes sense because it says how much heat is released. So our Q, which should be negative because we have energy being released, or how much heat is being released. All right, let's go ahead and continue on. Again, try the upcoming questions on your own first before you check the answers. So, number one, when a sample of ammonium thiocyanate is mixed with solid barium hydroxide in a glass beaker, the mixture changes to a liquid and the temperature drops sufficiently to freeze the beaker to the table. Which statement is true about the reaction? Okay, so we have our options here. We have to think about, is the process endo or exothermic, and therefore will delta H be positive or negative? Okay, so if we look at what we are given, we can see we're mixing two chemicals, and the mixture changes to a liquid. Okay, we had a solid to begin with, and it changes to a liquid, and the temperature drops sufficiently to freeze the beaker to the table. Okay, well, what could cause this to happen? Well, the process is endothermic and delta H is positive. okay, because we see the temperature drop, okay, the mixture changed to a liquid. Okay, we have a delta H that is positive, and a delta H that is positive means we have an endothermic process. Okay, the temperature decreased in this case. Okay, let's take a look at number 2. Which one of the following statements is true of all exothermic reactions? Right, so if we have an exothermic reaction, exo, think of exit, that means energy is leaving or being released, and therefore they give out heat. All right, let's continue on with our practice problems. All right, number 3. If 500 joules of heat is added to 100.0 gram samples of each of the substances below, which will have the largest temperature increase? Okay, so we have 4 different objects. Okay, we have gold, silver, copper, and water, and then the specific heat capacity of each is given. Now, one thing I want you to note is water's specific heat capacity is extremely high compared to these metals here. And you may be thinking, that's weird, but it actually takes a lot of energy to heat up a sample of water. Okay, so based on all of these results, which of these do you think would have the greatest temperature increase? Well, since water is really high, that means it takes a lot of energy. On the other hand, gold has a low specific heat capacity, which means it doesn't take a lot of energy. So since we're adding the same amount of energy, 500 joules, to the same amount of each of these samples, 100 grams, gold with the lowest specific heat capacity will have the largest temperature increase. All right, number 4. The temperature of a 5.0 gram sample of copper increases from 27 to 29 degrees Celsius. Calculate how much heat has been added to the system. The specific heat capacity of copper is given as 0.385. So you should go ahead and try to calculate this. Okay, think about what you are given, the mass, you know the temperature, both before and after. We're calculating how much heat. Okay, think about also, since the temperature is increasing, what does that mean? Well, if you do this correctly and you calculate your answer, you should get 3.85 joules. All right, let's take a look at number 5. This question is very similar to the previous question on specific heat capacity. Here we have 4 metals. Let's say we have a 1 kilogram sample of each metal at room temperature that is being heated by the same electrical heater for 10 minutes. Identify the metal which has the highest final temperature. Well, just like before, if we look at these, the highest final temperature means we're going to have the lowest specific heat capacity, and that would be CD, cadmium. And finally, we have number 6. The specific heat of metallic mercury is 0.138 joules per gram per degree Celsius. If 100.0 joules of heat is added to a 100.0 gram sample of mercury at 25 degrees Celsius, what is the final temperature of the mercury? So let's think about what we're given. We're given the specific heat. We know that 100 joules of heat is added. That means we know our Q. It's added to a 100 gram sample, so we know our mass. we know that the mercury is 25 degrees Celsius. So we need to know what is the final temperature. So there are two ways we could go about solving this problem. I'll just go over the way that is listed here. So if we know our Q equals mc delta T, we can solve for the change in temperature, the delta T, because we know Q, M, and C. So we know that the delta T is 7.25 degrees Celsius, and we get that after inputting what we already know. So since the change in temperature is 7.25 degrees Celsius, and we initially started at 25, that means our final temperature is going to be 25 plus 7.25, which gets us to 32.3 degrees Celsius. Okay, double check those sig figs for this problem.